Okay, picture this, if you will. You're in these snow-covered hills, and there's this machine humming away, almost like it's using, I don't know, magic physics.
Right.
We're actually talking about IBM's quantum computing research facility.
Mm-hmm.
Welcome to the deep dive. Today, we are really getting into the weeds on quantum computing. Its potential, this huge international race to get ahead, especially the U.S. and China, and crucially, what it means for cybersecurity.
It's a massive topic.
It really is. And we're basing our chat today on a transcript from The Future with Hannah Fry on Bloomberg Originals.
Okay.
So our mission for you listening is to get past the hype, you know?
Yeah, there's a lot of hype.
Totally.
Yeah.
We want to understand the basics, the stakes involved in this tech race, and fundamentally why you should probably care about it. All right, let's jump in. What is quantum computing? Why all the buzz?
Well, the fascinating thing, and this is key, it's not just about making our current computers faster. That's sort of a misconception. You know, classical computers use bits like simple on-off switches, right? They solve problems step by step. Think of someone feeling their way through a maze, one path at a time.
Got it. Sequential.
Exactly. Quantum computers, though, they use qubits, quantum bits. And the big difference, the really mind-bending part, is superposition.
Superposition, okay.
Yeah, a qubit can be kind of on and off at the same time or somewhere in between, like a dimmer switch, maybe, not just a stark on-off.
Right, not just binary.
Precisely. And it's this both-at-once thing that gives them their power.
So back to the maze analogy. Instead of trying one path, then another, a quantum computer could, what, check all the paths at the same time. That sounds huge.
It is. That's the potential leap. This parallel processing means they could, theoretically, solve certain problems in minutes, problems that would take our best supercomputers like millions of years. But as the source material points out, it's not just speed, it's deeper. It's a totally different way of working with nature at its most fundamental level because, well, nature is quantum mechanical.
Right, it's speaking nature's language almost.
Yeah.
So it's not just a faster calculator, it's working on the universe's operating system.
That's a good way to put it. And that opens up incredible possibilities for science.
Like what? What kind of breakthroughs are we talking about?
Well, think about designing new medicines. Imagine simulating how molecules interact so precisely you could create a drug that just targets cancer cells perfectly with hardly any side effects.
That would be revolutionary.
Absolutely. We just don't have the computing power for that now. The transcript mentions designing drugs at the level of atoms, creating totally new materials, batteries. Stuff we haven't had this before.
It feels like getting a new sense almost. The transcript compared it to the invention of the telescope, didn't it?
It did, and it's a really apt analogy. Quantum computing gives us this new window, a way to see and understand things at a scale that we just did not have access to before, especially down at the atomic and molecular level.
Okay, but let's keep our feet on the ground. Are they actually doing this now?
Well, that's the reality check. The source makes it clear, current quantum computers cannot yet perform useful calculations better than a supercomputer for, most things.
Right. Still early days.
Very early. Getting reliable answers, stable answers, even from a handful of qubits. It's described as phenomenally difficult.
So no quantum laptops just yet. What does one of these things actually look like? I'm picturing like a giant gleaming server room.
Yeah, the visuals can be misleading. That big, impressive setup, the big, shiny behemoth. Inside that, the actual quantum computer, the core of it, it's tiny. They show the Heron chip 133 qubits just sitting in someone's palm.
No way.
Yeah.
That's small for all that potential power.
Yep. But there's a catch, a big one.
I remember reading something about them being incredibly fragile.
Extremely. Utterly sensitive. To keep that quantum state stable, the chip has to be kept ridiculously cold, just fractionally above absolute zero.
How cold is that?
Colder than deep space. Colder than the background radiation of the universe. It's called the coldest thing in the known universe in the transcript.
Wow. Why so cold?
Because any outside energy, even the tiniest bit of heat, vibration, anything, can knock the qubits out of their quantum state and cause errors, wrecks the calculation.
Okay, so incredibly powerful potential, but incredibly delicate systems. Now, this brings us to the whole international competition. The transcript calls it a quantum arms race, U.S. versus China. What's going on there?
Yeah, that arms race framing really highlights the geopolitical significance. Countries see leadership here as strategically vital.
And IBM is a big U.S. player.
Huge. They're investing massively as part of this nearly $7 billion annual R&D budget they have. They're aiming to really unlock quantum's potential by, I think the transcript said 2033.
And the U.S. government sees this as critical.
Absolutely. The transcript notes the U.S. views that tech leadership, especially in quantum, is right up there with trade deals and military strength. It's geostrategic.
Okay, what about China? The numbers mentioned sound pretty big.
They are. The investment figures cited are over $15 billion. That's like more than 3 times any other single country. They've set up loads of research centers and apparently hold more than half of all the quantum tech patents right now.
So a different approach. The transcript mentioned China treating science as a national asset.
Yeah, it seems to be a more top-down, state-driven strategy, possibly leading to larger research teams, more coordinated efforts perhaps. A security expert quoted in the source mentioned U.S. researchers feeling like they're up against the funding of a nation-state.
That's a big difference. How's the U.S. responding?
Well, there are export controls stopping advanced U.S. tech from going to China, and also trying to boost domestic research funding, like through the GTTS and Science Act.
It really shows how science and global politics are tangled up here. IBM doesn't collaborate with Chinese companies, right? The transcript mentioned national security.
That's correct. IBM classifies quantum as a sensitive technology due to those national security implications, so no joint ventures there.
Interesting. Feels like maybe things were more open before, collaboration-wise.
Possibly. The source suggests that while the early research happened when international relations were maybe a bit warmer, the current tensions have definitely put a damper on collaboration in areas deemed strategic, like quantum.
Okay, so the race is on to build them, but there's this other huge angle the transcript brought up, the potential to break internet encryption. That sounds bad.
It's a very serious concern. The problem lies in how most current encryption works.
How did it work? Simply put.
Okay, very simply. It relies on math problems that are easy to do one way, but incredibly hard to reverse. Like multiplying 2 huge prime numbers together, easy for a computer.
Right.
But if you only have the result, finding those original prime factors, that's unbelievably hard for classical computers, especially when the numbers are hundreds of digits long, like in modern RSA encryption.
How hard?
The transcript gives a sense of scale trillions of years for a classical supercomputer, basically impossible in practice.
Okay, so our digital security relies on this difficulty. How do quantum computers change the game?
Remember superposition, doing many calculations at once.
Yeah.
Well, there's a specific quantum algorithm, Shor's algorithm, that's incredibly efficient at factoring large numbers. So, a powerful enough quantum computer could potentially do in, say, minutes what takes a classical computer trillions of years.
Minutes. That's terrifying. Think about banking, government secrets, everything.
Exactly. The transcript highlights the banking industry's concern. HSBC, for instance, they handle trillions in payments. A breach would be catastrophic.
What are their specific worries?
Well, everything from your personal account being emptied, identity theft on a massive scale, forged transactions, but also just a complete loss of trust in the digital financial system. That could be destabilizing.
And then there's this store now, decrypt later idea. That sounds sinister.
It is. Also called harvest now, decrypt later. The worry is that adversaries, maybe state actors, are already collecting encrypted data now, siphoning it off, storing it, and just waiting until they have a powerful enough quantum computer to break the encryption later on.
So today's secrets become tomorrow's open books. Who would be the main targets?
The transcript suggests national security infrastructure is probably top of the list. Imagine state secrets, intelligence operative identities, military plans, all suddenly exposed. The vulnerability is huge.
Okay, this is pretty scary stuff. What can we do? Are there defenses? The transcript mentioned something called QKD.
Yes, quantum key distribution. It's a potential way to create fundamentally secure communication.
How does that work? Is it quantum too?
It is. It uses quantum physics principles. Instead of relying on mathematical difficulty, it relies on the laws of physics themselves. Basically, you send encryption keys encoded onto single particles of light photons down fiber optic cables.
Single photons.
Yeah. And the core quantum idea is, if anyone tries to eavesdrop, to observe that photon to read the key, the very act of observing it changes it. It disturbs the quantum state.
So you'd know instantly if someone was listening in.
Exactly. The disturbance alerts the legitimate users, and they know the key's been compromised, so they just discard it and generate a new one. It's inherently secure against eavesdropping, in theory.
That sounds genuinely unhackable. Is it being used? The transcript mentioned
Right.
HSBC testing it.
Yeah, HSBC did trials with BT over their existing fiber network in London, securing financial data. There are other trials, too. Hospitals sending sensitive scans, governments looking at it for classified communication.
So people are taking this threat seriously.
Increasingly so. There's a growing sense of urgency. Some experts quoted predict we might see quantum computers capable of breaking current encryption, cryptographically relevant ones within maybe 5 to 7 years.
5 years, that's soon.
It's a plausible time frame, according to some, which is why the race for quantum-resistant solutions is heating up.
And this quantum security race is international, too. China is involved here as well.
Oh, yes. China has made significant strides in quantum communication. They launched a satellite back in 2016, MISHIS.
A satellite for QKD.
Yep. It demonstrated sending quantum keys over much longer distances than fiber allows, potentially linking cities across continents. It's part of their plan for a national, maybe even global, quantum network.
Are other countries doing this?
Yes, others are working on it too. Singapore, for example, is mentioned as developing commercial networks using smaller, possibly cheaper satellites. The goal is global, unhackable communication.
Firing single photons into space and back. It sounds like science fiction.
It does, but it's actively being developed, using satellites and telescopes to bounce these quantum keys around the globe.
It's incredible. But, framing it all as just a race, U.S. versus China, the transcript offered another perspective at the end, didn't it? Comparing it to the telescope again.
That's a really important point to circle back to. Yes, the geopolitical competition is real and intense, but underneath it all, quantum computing is a fundamental new tool for science.
Like the telescope opened up the universe.
Exactly. Quantum computing could let us see and understand the universe down at the level of atoms in a way that we have just never had access to before. It's about fundamental discovery.
So beyond the race, there's this potential for, well, all of humanity.
That's the hope. That ultimately this powerful new capability, this new way of understanding nature, will lead to breakthroughs that benefit everyone, regardless of who gets there first.
Okay, so let's try and wrap this up. What we've explored today is pretty mind-bending. Quantum computing isn't just faster computers. It's a different way of computing based on quantum mechanics.
Right, with huge potential for science, medicine, materials.
But also a major threat to the encryption that protects basically everything online.
Yeah, driving this intense race between the US, China, and others, not just to build the computers, but also to build new quantum-proof security like QKD.
And that telescope analogy really sticks. It's like we're getting a new lens to see the universe at its absolute smallest scales.
Which leads to a really big final thought for you, listening out there. Well, think about it. If this really is a fundamental shift, like the telescope or microscope, how could it reshape not just our tech or global power balances, but maybe even our basic understanding of reality?
And what other problems, things we think are impossible now?
Exactly. What might become solvable with this completely new kind of tool? What totally unforeseen things might emerge from this quantum frontier? Lots to think about.